Now we look at the notion of isomorphism. So we say that two objects are isomorphic if they're essentially the same, meaning that they basically have all the same parts. They're just kind of labeled differently, but they work the same way. So if you think back to your set theory or theory of proofs class, probably at some point you looked at finite sets, and you realized that any set with 3 elements is basically the same as any other set with 3 elements. I mean, they might be labeled differently, you know, representing different things or something like that. But any question you ask about, like, what do the subsets look like and blah, 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 they have exactly the same answers from the point of view of set theory. And that's what we look at now for linear algebra. So we say that an isomorphism is an invertible linear map. And then we say that vector spaces V and W are isomorphic, meaning, so iso here means same or equal, and then morph means shape. So they have the same shape, they're isomorphic if there exists an isomorphism between them. And so this isomorphism is going to be, you know, some T mapping from V to W, something like that. And then this is denoted by saying, whoops, I did it again. V is isomorphic to W. And sometimes people put a little T floating around somewhere nearby just to decorate it, but I don't. Okay, so the first theorem we have says that, well, it's a formalization of the idea that matrices are just linear maps, right? And so what we have is that this M thing that we've been slapping on to linear transformations actually is an isomorphism from the vector space of linear transformations over to the M by N matrices. Okay. And so the proof is not hard. So by 336 and 338, so these are properties of M as a transformation, the additivity and scaling properties. M is linear. To show invertibility, we use a basis of V's for V. And W's for W. Okay, so there's 2 parts for invertible. By the theorem, we can show that it's injective and surjective, and then we'll know that it's invertible. So for the injectivity part, suppose that M takes T to 0. So then by our characterization of injectivity for linear maps, we know that this can only happen if M is injective when T is the 0 transform, right? So we need to show that this implies T is the 0 transform. Okay. But then let's see. So if the matrix for T is equal to 0, then that means that by the definition of the matrix of a transform, TVK has to be equal to 0 for every element of the basis. And so if a linear transformation sends the entire basis to 0, then it sends everything to 0. Which means it's the 0 map. Okay, so M has a trivial null space, so it's injective. Now we look at surjectivity. Why is M surjective? Well, suppose we take a matrix, M by N matrix. What is the linear transform that gets mapped to this matrix? Can we find one? Yes, we can. We just define T in the way that works based on the definition of matrix of a transform. And so TVK, we define that to be, in terms of the matrix, the sum of the AJKs times WJ for each K. Then the matrix of T will be equal to A. And that's it. Boom, we're done. So it's real straightforward. I just want to take a moment to point out that even though the linear transforms from V to W is isomorphic to FMN, there's no God-given way to set up the correspondence. So I mean, even R as a vector space over itself is isomorphic to R, right? But you don't have to send 1 to 1. You could send 1 to -1. Or in fact, you could send 1 to 3. Those would both define an isomorphism from one to the other. And that's because -1 could be your basis for R, and 3 could be your basis for R, right? So it depends on your choice of basis. And keep in mind that as long as you don't have the trivial vector space, there are always many choices, because bases are highly non-unique.